Hi guys, in the previous lecture we discussed about the DC generators. So in this lecture what we will do is we will discuss upon different type of DC motors and what kind of question can be framed on DC motors in the GATE examination. So let us first discuss the first type of DC motor, that is your shunt motor. So in shunt motor, what is the basic circuit diagram? We have a resistance, that is your field resistance, armature EMF, armature resistance, and then the terminal voltage. Here, this is our IL, this is IA, that is armature current, this is IF, that is field current. This resistance is RF. So IF is basically VT upon RF since it is connected in parallel with VT. And by KCL, IL is equal to IA plus IF. Okay. And the other performance equation that we can write is, if this is EB, that is your back EMF, VT is equal to EB plus IA into RA. So these are the basic operating equations of a DC shunt motor. Now let us see the problem that is in front of us. A 4-pole 500 volt shunt motor has 720 wave connected conductors, which means Z is equal to 720. And since the winding is wave winding, number of parallel path is 2. Now full load armature current IA is 60 ampere. Flux is 0.03 Weber. Okay. Armature resistance is 0.2 ohm. And then brush drop is 1 volt. Is it fine? Now we need to calculate the full load speed of motor. So remember, whenever we talk about speed of motor, we have to take into consideration the back EMF or the induced EMF. So what is the expression for EMF? There can be two expressions, Vt minus Ia into Ra, which is also equal to phi n Z by 60 into P by A. Now what is terminal voltage? 500 volt as it is given. Ia is 60, Ra is 0.2. What is flux? 0.03. And we have to find number of conductor is 720 by 60. Number of poles is 4 and number of parallel path is 2. So how much will this become? 488 is equal to 12 into 0.03, 0.36 into 2, 0.72 into n. So n will come out to be, and one we have to take also the brush drop. So this will be 486. Okay. Brush drop is 1 volt per brush, and we know there will be 2 brushes, so it will be 2 volt. So n will come out to be 675 rpm. So remember, it is very easy to commit a mistake that you might forget to take the brush drop. So remember, usually the brush drop is 2 volt, and if it is given as 1 volt, please check if it is given per brush, because if it is given per brush, you have to take twice of that. Let us move on to the next problem. It is saying a 240 volt unsaturated shunt motor has an armature resistance of 0.04 ohm, field resistance of 100 ohm. Find what resistance must be added in field circuit to increase the speed from 1200 to 1500 when the supply current is 200 ampere. Now see, there are two methods of speed control, basic two methods. First one is armature control. Here what we do is, we basically control the terminal voltage applied to the motor. The second one is called as field control. In this what we do is, we vary IF is reduced so that speed is increased. So field control is used to control the speed of the motor above the base speed. What is base speed? That is your rated speed. Whereas armature control is used to control the speed of motor below the base speed or below the rated speed. Now in this problem, as you can see in the first part, it has asked us what resistance must be added in field circuit. If you add resistance in field circuit, the field current will reduce, so the flux will reduce and the speed will increase. That means the speed will increase from 1200 to 1500 rpm. Now as we can see, if there is no saturation, okay, it has written unsaturated, it means flux is proportional to IF. Now we know induced EMF is directly proportional to flux into speed, which means E2 by E1, flux is proportional to IF, so I have replaced flux by IF into N2 by N1. Is it fine? Now what is IF1? IF1 is 240 volt was applied, field resistance was 100 ohm, so it will be 2.4 ampere. So this means E2 by E1 will be equal to IF2, I don't know about this, by 2.4. N2 is 1500, we have to increase the speed to 1500 from 1200 rpm. Now what about E2 and E1? Now when we talk about E1, first we have to calculate IA1. Supply current was 200 minus field current. I just now told you the KCL equation that the supply current is equal to IA plus IF. So IA is supply current minus IF, which means E1 can be written as VT 240 minus 197.6 into 0.04. Is it fine? So now what about E2? Since the supply current remains same, it is saying supply current is 200 ampere. So armature current will be 200 minus IF2 into 0.04. Now let us plug these value into the equation that we wrote above. So it will be 240 minus 200 minus IF2 into 0.04 by 240 minus 197.6 into 0.04 is equal to IF2 by 2.4 into 1500 by 1200. From this what I get is 240 minus 8 plus 0.04 IF2 is equal to 120.88 IF2. From here I can calculate IF2. IF2 will come out to be 1.918 ampere. Once I have IF2, IF2 will also be equal to terminal voltage over RF plus R external, because we have connected an external resistance in series with the field. So 240 by 100 plus R external. From this if we calculate R external, it comes out to be 25.09 ohm. Is it fine? So that is how we can calculate the external resistance to be connected in series. What is the next part? With the field resistance as in the first part, find the speed when supply current is 100 ampere. Now I am giving you IL is 100 ampere. We know field current is 1.918 because field resistance is same as in part A, which means we have an external resistance in series with the field winding. If we subtract both, we will get the armature current, that is 98.082 ampere. Once we have this, what I can do? I can calculate the induced EMF. So induced EMF is Vt minus Ia into Ra. This will come out to be 236.076 volt. Now, since we are not changing or varying anything in the field, that means flux can be taken as constant. If flux is constant, EMF is proportional to speed, which means E2 by E1 is equal to N2 by N1. E2 is 236.076, E1 240 minus how much? This I will now take as E1, that is 240 minus 200 minus 1.918 into 0.04 is equal to N2. N1 will be 1500. Why? Because after adding the external resistance, the speed was 1500 RPM. Now, from this if we calculate N2, it will come out to be 1525.84 RPM. Is it fine? So, I have taken the first or the final condition of first case as the initial condition for the second part. That is, after adding external resistance, I have obtained the speed to be 1500 RPM. Now that I am taking as the initial speed. And now when I alter the field, the supply current to 100 ampere, I am finding the speed of the DC motor. Moving to the next problem, it is saying a 250 volt shunt motor with a constant main field drives a load, the torque of which varies as the cube of speed. When running at 500 RPM, it takes 40 ampere. Find the speed at which it will run if a 25 ohm resistor is connected in series with the armature neglect motor losses. Now see, whenever you see this line, neglect motor losses, it means armature resistance can be taken to be 0. Okay. Now it is telling us that armature resistance is taken to be 0, and it is telling that the torque of the motor is proportional to the cube of speed. Now initial speed is given to us as 500 RPM, armature current as 40 ampere, and terminal voltage, which will also be equal to EB. Why? Because RA is 0, is given to us as 250 volt. Now, for a shunt motor, I already know that the torque is proportional to Ia. Why? Because flux can be taken as constant until the supply voltage is constant. Okay. Till supply voltage is constant, you can take the flux as constant. Now we know torque is proportional to N cube as well as torque is proportional to Ia, which means I can say Ia is proportional to N cube. Is it fine? And since EB is proportional to N, it is also proportional to EB cube. Why? Because if flux is constant, EB is proportional to N. Is it fine? So now if we use this proportionality, so initial current is 40 ampere. Let us say final is Ia. Initial EB is 250. Final EB will be 250 minus Ia, and you have added a resistance of 25 ohm. This way I get a cubic equation in Ia. Okay. Once you get a cubic equation, if you solve it, you will get Ia equal to 5 ampere. Now what was the question again? We need to find the speed. For finding the speed, we need to find the induced EMF. So if Ia is 5, EB will come out to be 250 minus 5 into 25. That is 125 volt. Now we know EB is proportional to N. So 125 by 250 is N2 by N1. Initial speed was 500, which means speed will be 250 RPM. Okay, that is the speed is just halved if the torque varies as the cube of speed. So as you can see, in case of DC motors, it is all about the equations and where to apply each equation. So it is better that if you write down the data that is given to you first, so that you can attempt the problem with a clear mindset. Moving on to the next type of motor, that is series motor. So here what will happen is, the equivalent circuit will be something like this. This will be armature resistance. This will be series field resistance. This will be VT IA. So here, first of all, field current is equal to armature current. That is why torque is proportional to IA square and EMF is proportional to IA into N. And what about performance equation? It is equal to EB plus IA RA plus R series. Okay. So these are the equations that we generally use in case of a series motor. Now let us see what is the problem that is given to us. A 4-pole, so I will keep on writing down the data. 4-pole series wound fan motor. So remember, whenever you see a fan motor, torque is proportional to N square. Runs normally at 600 RPM. So N1 is 600 RPM. Supply voltage is 250 volt. And it takes an armature current of 20 ampere. Now field coils are all connected in series. Okay. Estimate the speed and the current taken by the motor if the coils are reconnected in two parallel groups of 2 in series. See what happens. If coils are connected like this, earlier all 4 were in series. So earlier the MMF would be N series into IA. But now, here we will have IA, here we will have IA by 2 and IA by 2. Okay. And we have half the number of turns in each branch. Which means the overall MMF will be, so see, earlier flux was proportional to IA, now it is proportional to IA by 2. So if you divide the coils in parallel groups, you can change the flux. So it is one method of speed control, that is by changing the flux, or we can say field control. Okay. Now the load torque increases as the square of speed, as I told you, since it is a fan motor. Assume flux is proportional to current and ignore losses. Again, ignore losses is given, that means armature resistance is 0 as well as series field winding resistance is 0. Now if such a thing happens, it means VT is equal to EB, which means back EMF remains constant. Now if back EMF is constant, it means IA1 into N1, I mean flux into speed will be constant. Now in the second case, when you have connected two coils in parallel, the flux will be proportional to armature current by 2. Now armature current can change, that is why I have used different variables IA1 and IA2. Is it fine? So this part is very important. When you connect field coils in parallel, the flux is proportional to half of the current. Now once we have established this, what I can write down? IA2 is equal to IA1 into 2 into N1 by N2. Now N1 I already know, it is 600 RPM. IA1 I already know, 20. So 20 into 2 into 600, that is 40 into 600, 24,000 by N2. So that is the first relation that I have derived based on the armature current. Now there are two variables IA2 and N2. We need another relation. How we can derive that is, we know that torque is proportional to N square, and we know in case of series motor, torque is proportional to IA square. Is it fine? So in the first case, IA1 square is proportional to N square. But when you have connected two coils in parallel, I know flux will be proportional to half of the armature current, which means IA2 square by 2 is proportional to N2 square. Now how can I say this? See, torque is always proportional to field current into armature current, or you can say flux into armature current. In the second case, flux is proportional to half of the armature current, that is why IA2 square by 2. Once I have this information, I can divide both the equations. What I will get? IA1 square into 2 by IA2 square is equal to N1 square by N2 square. From this I can establish IA2 is root 2 IA1 into N2 by N1. Okay? Or I can say root 2 N2 by 30. This will be my second equation. The first one was IA2 is 24,000 by N2. Now I have two equations and two variables. From this I can calculate speed as well as armature current. So what will be the speed if we solve these two equations? Speed will come out to be 713.52 RPM and armature current will be 33.635 RPM. Is it fine? So that is how we can calculate armature current and speed for the case of a series motor in case of field control. Let us see another problem based on series motor. It is saying a 4-pole series motor, that is PS4, has 944 wave wound armature conductor, that is Z equal to 944. Since it is wave wound, A is equal to 2. At a certain load, flux per pole is 0.0346 or 34.6 milliweber and developed torque is 209 Newton meter. Calculate the line current taken by a motor and the speed at which it will run if terminal voltage is 500 volt and total motor resistance, that is Ra plus R series, is 3 ohm. So that is all the data that is given to us. Now, since it is the developed torque, I can find out developed power. Now developed power is developed torque into omega. That is 209 into 2 pi by 60 into n. That is our developed power. Developed power in any machine is basically the product of back EMF into armature current, which will be 209 into 2 pi n by 60. Now how do you write back EMF? Terminal voltage minus IA into resistance, 209 by 60 into 2 pi n. Now this way I have got a relation between the speed and the armature current. So from here if we calculate the equation for speed, n will be equal to 500 minus 3IA, okay, into IA into 0.91848. Okay, that will be basically the speed that we can find out. Or let us write this equation as it is. So let me mark this as first. Is it fine? Now let us find out another equation because we have two variable IA and N. Back EMF is basically Vt minus IA into Ra, or Ra plus R series in case of series motor. This will also be equal to flux 0.0346 into N, that is speed, into Z 944 by 60 into P by A. P by A will be 2. So 500 minus 3IA will be equal to 0.0346 into 944 into 2 by 60 into N, which means N will be equal to 500 minus 3IA into 0.91848. Now once we have two equations in two variable IA and N, these equations can be solved how? You will substitute the value of N here in order to determine IA, and once you do that, you will find out the value of IA and N. IA will come out to be 20.1 ampere, whereas speed will come out to be 403.85 RPM. So whenever we are talking about the speed control of a DC motor, we have to play around with two variables, that is armature current and speed. So since you want to find out two variables, you have to form two equations in some way in order to find out the speed. Moving on to the next type of problem, that is based on losses inside the DC motor. So what are the different type of losses? We have copper losses, that is IA square into Ra. We have core loss, hysteresis plus eddy current. We have field loss, that is either IA square into RSC or Vt square by Rf. We have rotational loss, that is PR, rotational. Okay, so these are the different type of loss that can occur in a DC machine. Now as we saw in case of transformer, when we talk about core loss, hysteresis loss is proportional to frequency, whereas eddy current loss is proportional to frequency square. Now in a DC machine, there is no concept of frequency, which means we have to take speed. So hysteresis loss is proportional to speed and eddy current loss is proportional to speed square. Now this problem is based on core losses, so let us see it. The hysteresis and eddy current loss in a motor running at 1000 RPM are 250 and 100 watt. So I know hysteresis loss is some constant into speed, which means this constant is 250 by 1000 or 0.25. Similarly, eddy current loss is some constant into N square, which means Ke is 100 over 10 to the power 6, 10 to the power minus 4. Now it is saying if flux remains constant. Since flux is constant, that is why I can directly write this. Find the speed at which the total iron losses will be halved. If total iron losses are halved, it means iron losses will become 250 plus 100 by 2. That is 175. Now 175 will be equal to Kh into N, 0.25 N, Ke into N square, 10 to the power minus 4 into N square. From this we have to find the N. This is a quadratic equation. So N will come out to be 570 RPM. That is, at a speed of 570 rpm, your core losses will be halved. Now, once we have a knowledge of the losses inside the machine, we can also go for efficiency. Now, let us see this problem that talks about efficiency of a shunt motor. It is saying a 600 volt DC shunt motor, this is our terminal voltage, drives a 60 kilowatt load. That is your P out, because it is talking about load power at 1000 rpm. Field resistance 100 ohm, armature resistance 0.15 ohm, stray loss is negligible, motor efficiency is 85%. Now, eta is 0.85, which will be equal to output power upon input power. Now, what will be this input power? It will be 70588.235 watt. Now, once we have a knowledge of input power, we can determine loss. What is loss? Input minus output. So, this will come out to be 10588.235 watt. Now, I have loss, but this loss will be a sum of rotational loss, armature loss, as well as the field loss. But we are only interested in the rotational loss. Now, once we have input power, I can also calculate the supply current. It will be equal to input power divided by the terminal voltage. Because in a DC motor, the input power is Vt into IL. So, this will come out to be how much? 117.647 ampere. Now, once we have IL, we can also calculate IA. That will be IL minus IF. IF will be how much? So, IL minus IF. IL is 117.647 minus IF 600 by 100. 111.647 ampere. Now I have IA. So what I can do is, I know this total loss is rotational plus field. In shunt motor, field loss will be Vt square by Rf plus armature copper loss 117.647 square into 0.15. 10588.235. From this I can calculate rotational loss to be 5.118 kilowatt. Okay. So that is how we can calculate the rotational loss. Next, it is asking us to find the speed at the no load condition. So one thing that you should always remember, at no load, output power is 0, which means developed power, which is equal to output power plus rotational loss, becomes equal to rotational loss. So under no load condition, the developed power is always equal to the rotational loss. So now it is asking us the speed at no load. I know the developed power is 600 minus armature current into armature resistance, that is EB into IA, is equal to rotational loss 5.118 kilowatt. Once I have this, I can calculate IA from the solution of quadratic equation, that is 8.549 ampere. When I have IA, I can calculate EMF 600 minus 8.549 into 0.15. It will be 598.72. Now, why I have calculated EMF? If you want to calculate the speed, you have to go through EMF. Now, earlier the EMF was how much? Earlier the EMF was coming out to be 600 minus 111.647 0.647 into 0.15. Now the EMF is 598.72 is equal to, earlier the speed was 1000 RPM. I need to find the speed now. So N2 will come out to be 1026.51 RPM. Also remember, this value should always be greater than 1000. Why? Because 1000 RPM is the speed under loaded condition, and always the no load speed is greater than the speed under loaded condition. Is it fine? And here we have taken flux as constant because it is shunt machine, which means the speed is proportional to the induced EMF. Let us see another problem based on efficiency. It is saying a 200 volt 70 ampere 1000 RPM series motor, okay, has following full load losses expressed as a percentage of motor input: armature ohmic loss, field loss, rotational loss. Now the motor draws half of the rated current at rated voltage, which means input power is half of the full load power. Because voltage is rated but current is halved, we need to determine the speed in RPM and the shaft power output. Now, what is the input power under full load? That is 200 into 70. That is 14,000 watt. Now, what is the input power now? It is half of this, 7,000 watt. Now, these losses. So what is the copper loss? Since armature resistance and the series resistance are connected in series, it is 5% of full load, or we can say 5 by 100 into full load power, that is 14,000. So that is 700 watt. From this I can calculate RA plus R series, as it will be copper loss by IA square. Under full load, armature current is 70 ampere. So 700 by 70 square, this will be 0.14285 ohm. That is the sum of armature resistance and the series field resistance. Once I have this, I can calculate EMF. Again, why I am calculating EMF? Because I want to find the speed. So that will be Vt minus Ia into 0.14285. So this will come out to be 190 volt. Now we know we have halved the current. That means Ia now becomes 70 by 2, that is 35 ampere. From this I can calculate the new EMF. What will be new EMF? The new EMF will be 200 minus 35 into 0.14285. Because this resistance shall remain same, this will be how much? 195 volt. So now, once I have both the EMF, I can apply proportionality. What is the proportionality? EB2 by EB1 is equal to phi2 by phi1 into N2 by N1. In a series machine, flux is proportional to Ia. So EB2 by EB1 is Ia2 by Ia1 into N2 by N1. EB2 by EB1 means 195 by 190. Ia2 by Ia1 means 35 by 70. N2, I want to find out, N1 is 1000 RPM. From this, N2 will come out to be 2052 RPM. Now it is asking us to find the shaft power output. Now I have EB, I have Ia. From this I can calculate the developed power. EB is 195 into 35. Now what about rotational loss? It is 2% of the full load. 2 by 100 into 14,000 was the full load input. So it will be 280 watt, which means shaft power will be 195 into 35 minus 280. Okay. So that will be basically your shaft power, which you can calculate. Now let us talk a bit about the maximum efficiency condition in a DC machine. For maximum efficiency in a DC machine, the condition is constant loss is equal to variable loss. So what I shall do is, I will take a long shunt machine Y. I will derive the condition for long shunt, which can then be used to derive the condition for shunt as well as series, because in compound machine, if you remove the series winding, it is shunt. If you remove the shunt winding, it is series. So what shall be our model? This is our shunt resistance. This is our series resistance, armature resistance, armature EMF, and this will be our terminal voltage. So I am taking it as a generator, IA, IL, which means our output power will be VT into IL. Okay, this condition basically is invariant under generator and motor. Condition shall be same. Now let us figure out the losses. Now loss will be across the shunt winding, which is VT square by R shunt, or we can say, or you can write as IF square into R shunt. Then across the series winding, IA square RA plus RSE. Then across the rotor, that is your rotational loss. These will be the three loss. So what shall be efficiency? Output power divided by output power plus losses. Okay. Now for maximum efficiency, you have to differentiate this efficiency with respect to IL, and it should come out to be 0. Under this case, the efficiency shall be maximum. Now when you are differentiating, let us differentiate this. Let us see what shall come out. So the derivative, first differentiate numerator multiplied by denominator okay, minus differentiate the denominator multiplied by numerator. The derivative of first term will be Vt. Differentiation of Vt square by R shunt will be 0. What about this? IA can be written as IL plus IF. So it will be 2 times IL plus IF, because derivative of x square is 2x. RA plus RSE. Derivative of rotational loss will be 0. This should be 0. Now once we have come up to this point, what I will do is, I will cancel out the corresponding terms. So this shall get cancelled out. Divide entire equation by Vt. So what you will get? Vt square by R shunt plus IL. You can combine these two terms. Take out RA plus RSE common, and IA, which is IL plus IF, take that out also. So what you will be left with? 1 IA, that is IL plus IF, minus this IL is left here with 2 IL, plus this term will be left over, P rotational is 0. Now this will become IF minus IL. So Vt square by R shunt plus Ra plus Rse, it will be If square minus Il square plus P rotational equal to 0, which means Vt square by R shunt plus If square into Ra plus Rse plus P rotational equal to IL square into Ra plus Rse. Now on the left hand side, if you see Vt square by R shunt, that is a constant loss. Field current square into Ra plus Rse, that is also a constant loss. P rotational is also a constant loss. So what is the variable loss? That is IL square into Ra plus Rse. So that is the condition, constant loss is equal to variable loss. Now let us see for shunt. For shunt, what you do is keep Rse equal to 0. So what it will become? If square into R shunt, Vt square by R shunt can be written as If square into R shunt plus If square into Ra plus P rotational is equal to IL square into Ra. For series, make R shunt equal to infinity. So this loss will be 0. So it will be If square into Ra plus Rse plus P rotational is equal to IL square into Ra plus Rse. Now this term will go to 0. If, which is Vt by R shunt, I have taken R shunt to be infinity, which means P rotational is equal to IL square Ra plus Rse. Now what about separately excited? For separately excited machine, take Rse to be 0. Okay. From the series machine, if Rse is 0, so IL square into Ra is equal to P rotational. Is it fine? Now for series and separately excited, IL is basically equal to Ia. So that is the condition for maximum efficiency in case of any of the DC machine, that is constant loss is equal to variable loss. The same condition we saw in transformers where core loss is the constant and the copper is the variable loss. So core loss was equal to copper loss. Moving forward, next let us see the problem based on breaking of DC motor, that is the phenomena of plugging. In plugging, what we actually do is we reverse the armature terminals. That is, the armature supply voltage is reversed, due to which current will flow in opposite direction. In a DC motor, what happens? Armature current is generally Vt minus Eb by Ra. Now if you reverse Vt, it will become minus Vt plus Eb by Ra. That is, the current magnitude increases and it becomes negative. Now current magnitude will be very high because voltage and EMF are connected in additive polarity. That is why we connect an external resistance in order to limit the armature current during plugging. Now when current is flowing in reverse, in plugging what happens? The stored kinetic energy in the rotor and the supply power both are dissipated as copper loss. Okay. It will keep on absorbing power from the supply as well as the stored kinetic energy, and both will be converted to losses or will be dissipated as heat. Whereas when we talk about regenerative braking, the stored kinetic energy is delivered to the load as electrical power, but not in this case. So let us see the problem based on plugging. It is saying a 240 volt DC shunt motor draws 15 ampere, that is IL is 15 ampere. Terminal voltage is 240 volt. Supplying rated load at a speed of 80 radian per second. Okay. Armature resistance is 0.5 ohm. Field resistance is 80 ohm. Once I have field resistance, I can calculate field current. 240 by 80, that is 3 ampere, which means armature current is IL minus IF, 12 ampere. It is asking the net voltage across the armature resistance. For that, first let us calculate EB. That will be VT minus IA into RA, that is 234 volt. Now we know when we reverse the armature terminal, EMF and the terminal voltages are added. So voltage across the resistance will be 240 plus 234, that is equal to 474 volt. That is basically the first part. It is saying if external resistance is connected in series with the armature to limit the armature current to 125% of the rated value. As I told you, armature current becomes very high, so we have to connect an external resistance, which means it is saying the new armature current should only be 125%. That is 1.25 into rated, that is 12. So how much will this become? 15 ampere. For that we need to find the external resistance. The external resistance will be, that is voltage across the resistance by current. So from here we can find external resistance, which comes out to be how much? 31.1 ohm. Next it is asking the value of plugging torque and the braking torque. See, usually in a DC machine or any kind of rotating machine, the dynamic equation is this. Now once you are reversing the armature terminals, the motor torque is reversed. If the motor torque is reversed, Tm will be negative, so it becomes. So this motor torque is known as plugging torque. This is your load torque. And the sum of these two is called as braking torque. So we have to deal with three torques: braking torque, plugging torque and load torque. So how do you find the torque? Basically, developed torque is nothing but developed power by omega. If you neglect the rotational losses, the load torque is same as the developed torque. So first, initially, before plugging, the developed torque is equal to load torque. Developed torque is how much? Induced EMF, that is 234, into armature current, that is 12, divided by speed. Okay. So how much will this come out to be? 35.1 Newton meter. What about plugging torque? Once the armature current is reversed, it is limited to 1.25 times the rated current. Speed will be same, 80. So it will come out to be 43.875 Newton meter. What about braking torque? It will be sum of the two. It will be 78.975 Newton meter. So clearly remember the difference between the braking torque and the plugging torque. Braking torque is basically the sum of plugging torque and the load torque. Moving on to the last kind of problem that can be asked in GATE examination is Hopkinson's test. In Hopkinson's test, what we do is we connect two DC machine, one a motor and a generator, which are electrically as well as mechanically coupled. So what happens? The DC motor will act as a prime mover for the generator, and the generator current will act as the input to the motor. So both machines will drive each other, and the losses in the system will be taken from the supply, which means in Hopkinson's test, supply power is equal to losses, and the two machines will keep on running each other. Now it is saying two identical DC shunt machine when tested by Hopkinson's method gave the following result. Line voltage, that is 220 volt. Line current excluding the field current is 30 ampere. See here, This is the field current for motor. Here we will have field current for generator. So the line current excluding the field current is 30 ampere. Now the field currents are given as 4 ampere and 3 ampere. Now which one is the field current for motor and generator? We know EMF is proportional to field current into speed. Since both are mechanically coupled, speed will be same. So which will have higher EMF? The machine having the higher field current will have higher EMF. Now we know generator has to supply the current to the motor in order to run it, which means generator must have higher voltage than motor, because current always flows from higher voltage to a lower voltage, which means 4 ampere is the generator field current and 3 ampere is the motor field current. Now it is saying motor armature current is 220, which means generator armature current is 190. I have just applied KCL. 30 ampere is coming from here, 190 from here. So 220 will go into the motor. Now since we have excluded the field winding while taking the line current, so we will exclude the field loss. Now I know input power is equal to loss. What is input power? Line voltage into line current excluding the field current. It will be equal to copper loss plus rotational loss. Now what is the copper loss for DC motor? Armature current into RA. RA is given to us as 0.02. Copper loss for DC generator, armature current into 0.02. And it will be 2 times rotational loss. Rotational loss for generator and motor, both will be same because both are identical and both are mechanically coupled, so both are running at the same speed. From this equation, I can find out rotational loss. It will be 2455 watt. So that is the basic use of Hopkinson's test in order to find the rotational losses. Now we need to find efficiency of both machines. Now when we talk about generator, in generator IL is IA minus IF. So IA for generator was 190, IF was 4, so 186 ampere. So when you talk about efficiency, output power is VT into IL, 220 into 186 by 220 into 186 plus losses. Copper losses 190 square into 0.02. Field loss will be 4 square into, or let us directly write VT into IF, 220 into 4, rotational losses 2455. So this efficiency of generator will come out to be 0.931, or we can say 93.1%. What about motor? In case of motor, IL is IA plus IF, which is 220 plus 3, 223 ampere. So what about efficiency of motor? That is input power minus loss. What about the loss? 220 square into 0.02. Field loss 220 into 3. Rotational loss 2455. Divided by VT into IL, that is how much? 220 into 223. So from here the efficiency of motor is 0.9167, or we can say 91.67%. So remember, for Hopkinson's test, the input power is always equal to losses of both the machines. So these are the kind of problems that can be framed in gate examination, both based on DC motor, and in this the speed control of DC motor is most important. You can be asked questions based on speed. Is it fine? So this is all from this lecture.